Hello everyone. So our today's topic will be evidence for the quantized electronic energy levels, atomic spectra. Before going further, let us first discuss something. So we all know that speed of light, depends on the nature of medium. So when light passes through a medium, it gets deflect or it deviates from its original path. So suppose what is present in this figure. So when light pass, it get refracted or deviate, or bend. We can say bend. So light, when it passes from through a medium, it deflect or deviate. So when a ray of light is passed through a prism, we can see it, that it get deflect, and then it gives a spectrum of colors, known as VBA, violet, indigo, blue, green, yellow, orange, and red. So actually so the light, or the waves, with a shorter wavelength, they bends, more than the light or waves, with longer wavelength. So red color has higher wavelength and it hardly bends, when but violet, it has shorter wavelength and bends, or deviate more than the red wavelength or red wave, of light. So when a white light, this is in yellow color, but if you draw white, it won't be visible, so imagine it to be white. So when white light pass, through a prism, the wavelength with shorter wavelength, they bend, more, and the longer wavelength, example red, they deviate, hardly. So violet, the wavelength is 7.50 into 10 to the power 14 hertz, and for red 4 into 10 to the power 14 hertz. So this series of color or bands, we call it as spectrum. So this spectrum of color, or bands of these 7 colors, can be detected in the detector of film, or so when we look at it, it will look like this, the film will look like this. And when we look at each colors, each colors do not look like very distinct, okay, like they look like they are merged, okay, or merge, or we can say blend, okay. So this red and orange, they look like they are blended together or merged together, even orange and yellow, okay, and the rest of the color, okay, look like that when we look at the rainbow also. So we call it this, okay, spectrum to be continuous, okay, since they look like they are merged, okay. So like red merges with orange, orange merge with yellow, and so on. Let's discuss one more thing. So an object, okay, can, or atom or molecules, okay, they can absorb electromagnetic radiations, okay, and get excited, okay, to a higher energy levels, okay. Example, electrons, okay, they can get excited to a higher energy levels, okay, we can say excited state, okay. So they are unstable on the excited state, so while coming back to the, okay, ground state, okay, means their normal state, okay. So they emit radiations, okay, when coming back to the ground state they emit radiation. So atoms or molecules, okay, in atoms or molecules, these electrons, okay, they get excited, okay, and then after absorbing radiation or electromagnetic radiations, they get excited, and then they come back to the ground state, giving off energy, okay, or radiations. So let us suppose, okay, a sample, okay, absorbing white light, okay, and then it will give absorption spectra, okay. So when we suppose a gas, okay, an atom, okay, in a gaseous state, okay, when we suppose that it absorb, okay, certain quanta of photon or light, okay. So absorption spectrum will give, okay, this color, okay, in a film, okay, they will give these colors, and as you can see some black, okay, black lines, okay. So these gaseous atoms, okay, they absorb certain frequency of light, okay. So since they absorb certain frequency, okay, if we consider these, okay, atoms, okay, to be gas, okay, so they absorb certain frequency, and that is how they appear like a line, okay, black lines. So the opposite of this will be emission, okay. So excited molecule or atom, okay, so when these molecules or atom are excited, they gain energy, and after gaining energy they come to the ground or normal state by giving off radiations or energy. So emission spectrum, okay, So when they give off energy, they emit, okay, certain spectrum. Okay, so this certain spectrum are represented by this line, okay, single lines. So we call this line as spectral lines also, or atomic spectra. Okay, these lines, okay, on emission, okay, they give certain lines, okay, separated by these black spaces, okay, black. So we come to the conclusion that every atom or every elements, okay, they have certain particular lines, okay, spectral lines, and those are the characteristics, okay, of those elements, okay, or we can say it is like a fingerprint, okay, like we can, every human show different fingerprint, and we can have unique fingerprint, okay, to identify each person, okay. So every element has different these spectral lines, okay, characteristic spectral lines, okay. So through these spectral lines an element can be detected, okay. So the study of this emission and absorption spectrum is known as spectroscopy, okay. Study of emission spectrum or absorption spectrum is known as spectroscopy. So these lines, okay, as we have discussed earlier also, okay, these lines can be used to identify unknown atoms, okay. Okay, a scientist, Robert Bunsen, okay, was the first to investigate, okay, line spectra to identify elements, okay. Through this line spectra, okay, he identified elements, okay. He was the first to do that. Elements like rubidium, cesium, thallium, indium, gallium, and scandium, okay, was discovered using this line spectrum, or we call it as spectroscopy, okay. Helium, okay, the element, okay, this element, okay, present in the sun, okay, was also discovered through spectroscopy. So as you can see this sketch pen, okay, so it has lemon yellow and red color. So in the presence of light, okay, since this is red, okay, so in the visible light, okay, in the visible region, okay, it will absorb the rest of the color except the red, okay. So this red in the visible region gets reflected, and that's how we see this red color. Even this lemon yellow, it will absorb the rest of the color, but except for this, okay. So this is reflected and we see, okay, with our naked eyes, okay, this reflected color, okay. So that's how it appear as lemon yellow. Next topic will be line spectrum of hydrogen. Line spectrum of hydrogen. So when electric discharge, okay, is passed through gaseous hydrogen, the hydrogen, okay, molecule dissociates, like electric discharge. Gaseous hydrogen molecule. So hydrogen molecule, it breaks, okay, and it get excited, okay, or it absorb energy, okay, and then emit electromagnetic radiation. Writing in short form, radiation. So in presence of electric discharge, or when electric discharge is passed, hydrogen, okay, gas dissociates and they gain energy, and after that they emit electromagnetic radiation of discrete frequency, okay. So this spectrum, okay, is exhibited by the hydrogen, okay. So this spectrum consists of several series of lines, okay, like we have discussed in the atomic spectra also. Each atom has each characteristic spectral lines, so therefore hydrogen also exhibit its characteristic spectral lines. So when we look at hydrogen, it has one electron, okay, and one proton. So hydrogen is supposed to show, since it has only one electron, hydrogen is supposed to show only one spectral lines. However, it is not true. Belmer, okay, Belmer. So, okay, hydrogen, okay, exhibits spectral lines in the visible region, okay, and gave a relations on wavelength, okay. 677 1 by n 1 by 2 square 1 by n square centimeter inverse. Okay, let me write again here. So he found out these spectral lines of hydrogen, okay, in the visible region, okay, it's red, green, blue, violet, okay, in the visible region, and gave this wave number, okay, relations. So after his discovery, okay, many people, okay, discover that hydrogen show different spectral lines, okay, in the in different regions of electromagnetic spectrum, like ultraviolet, okay. So hydrogen also show spectral lines in the invisible region also, okay. Invisible region means it is not visible in our or through our naked eyes. So here n is an integer, okay, is an integer, and is equal to or greater than, okay, equal to or greater than 3. So n is equal to 3, 4, 5, and so on. So after the discovery of different spectral lines, okay, apart from the visible region, Rydberg, okay, modified these Balmer relations, okay, to 0.9 by n 1 square minus 1 by n 2 square centimeter inverse. So here n1 is 1, 2 like this, n2 n1 plus 1, n1 plus 2, and so on. So Rydberg gave this, okay, value, he modified this value, and this 10967 is also called Rydberg constant. So when we consider a atom, okay, it has a nucleus, okay, and concentric orbit, okay, around it, okay, where the electrons is present, okay, in this free energy. I hope it is not that clear, I think, but try to understand. So electrons, okay, let us suppose this electron is in the ground state, okay, after gaining energy it is excited, okay, to second energy state, okay, E2, okay, still on further absorbing higher energy, okay, it moves to E3, okay, or energy state E3, and then further gaining or absorbing radiation, electromagnetic radiations, okay, get excited to higher energy, okay, E4. So in this series, okay, N1, okay, N1, okay, So an electrons, okay, gain energy, okay, and get excited to higher energy state N2, okay, and then after gaining it comes back, okay. So this is represented by these arrow lines, okay. So it can either energy gain energy, okay, to a higher extent and then move to N3, okay, or energy level E2 and come back, okay, after gaining energy and irradiation, okay. So likewise it goes on, okay, and come back to the ground state, okay. Electrons from this orbital, okay, this orbital, okay, gains energy and come back again. And electrons can also, okay, gain energy and come back to from N4 to N3, okay, N4 to N3 shell, okay, or you can go back here like this, okay, or like this. So those electrons, okay, from N3 come back to N2, okay, they are in the visible region, or from N4 to N2, okay, or N5 to N2, or N6 to N2. So those coming, okay, above N2 levels, they are in the visible regions, okay, and they are called Balmer series, okay, Balmer series. So here you can see, okay, Bastian series also, okay, from N2 to N3, sorry, N4 to N3, N5 to N3, N6 to N3, like that. So even bracket, okay. So these are the series, okay, Lyman series, Balmer series, Bastian, bracket, and Fun, okay, series, okay. So here N1 value is 1, 2, 3, okay. So N2 will be always greater than N1, okay. So 2, 3, 3, 4, 5, 6, okay, 6, 7. The Lyman falls under ultraviolet, okay. Balmer visible regions, okay, and then the rest infrared region. So although hydrogen has only one electrons, okay, it shows different spectral lines in the visible and ultraviolet and infrared regions. Ultraviolet and infrared regions, okay. So we can say that each atom has each characteristic spectral, or each element has its characteristic spectral lines. So through this okay, discovery, was he imagined, okay, that each atom has discrete the idea of quantization, okay, from this theory and this discovery, okay, led to the idea of Bohr's model of atom. So through this Bohr's imagined atom, okay, we have a quantized energy levels.